Okay, for this section we're going to be focusing on the resistance of a wire. And one of the things that a resistance of the wire depends on is the material of the wire that it's made of. And this is referred to as the resistivity. It's a characteristic of a material that depends on its electronic structure and temperature. As we discussed last unit, wires are normally good conductors of electricity, so they allow electrons to move through them easily. The reason why they allow them to move through them easily is because the way that the atoms are actually bonded to each other. When we think of good conductors, we normally think of metals, and metals are bonded by this moving of electrons between the atoms themselves. So that's why the electrons can move through them easier. Now, if we look at a given wire, there's actually going to be four things that depend on the resistance of the wire. The first one is going to be the length. And if you were to increase the length, that would cause the resistance of the wire to increase. We were thinking about that. If you make the wire longer, then those charges that are moving through it are going to have to go through a greater distance, and there's going to be more obstacles in the way, so therefore the resistance would increase. Second factor is going to be the thickness, or the area, the cross-sectional area of the wire. And if you were to increase the area, that would cause the resistance of the wire to decrease. When we think about a wire, if we were to make it wider, then the electrons can move through there. There's more space for them to move through, so therefore ultimately the resistance would decrease. The third factor that's going to affect the resistance is what the wire is actually made of, or the material. And this is referring back to that resistivity. The symbol for resistivity is the Greek letter rho. It kind of looks like a P there. Normally when I draw it, I kind of draw it more like with a P with a tail there. If you were to increase the resistivity of a wire, that would cause the resistance of the wire to increase. Now, the resistivity is referring to the conductivity of a specific wire. The greater the resistivity, as we just mentioned there, the greater the resistance of the wire. If you look on your reference tables, at the bottom of page 5, there's this table. And it's just 6 different common, notice that they're all metals, and 6 metals that are typically used in wires. If you look here, the one with the smallest resistivity is silver. So therefore, it's actually the best conductor of electricity out of the 6 listed here. On the other hand, nichrome, just right above it, would be the worst conductor of electricity, because it has the highest resistivity based on this table here. Fourth factor that's going to affect the resistance of a wire is going to be the temperature of it. If the temperature of the wire was to increase, that would cause the resistance of the wire to increase as well. These 2 little animations do a nice job kind of explaining that. If you think back to chemistry, when a wire or a material is heated up, it causes the molecules or the atoms of that to move faster. And because the molecules or atoms are moving faster, the electrons that are flowing through them won't be able to get around them as easily. On the other hand, if it's a nice cool conductor, they won't be moving as fast, so the electrons can flow through them faster, as you see in this animation. Now, based on the resistivity, the length, and the area, we can calculate the resistance of a wire at a given temperature using this equation. The resistance of the wire, capital R, is equal to the resistivity times the length of the wire divided by the area of it. Let's just go through and go over the units for each one of these. Area would be measured in meters squared. Length would be measured in meters. Resistivity would be measured, if you look on your reference tables, those constants are ohms times a meter. And resistance is going to be measured in just ohms. So dimensionally how that works out is because resistivity is ohms times a meter, length is a meter, and then area is meters squared. Well, this meter squared cancels out with each one of those meters, leaving just ohms for resistance. Let's take a look at these two examples. It says determine the resistance of a copper wire that has a cross-sectional area of 2 times 10 to the negative 3 meters squared, and it's 40 meters long. Okay, so we write down our givens here. We know that the wire is first made out of copper. So because we know the material, we can look up what the resistivity of the copper wire is. The resistivity for copper wire is 1.72 times 10 to the negative 8 ohms times a meter. We also know the cross-sectional area of it. So that's A, and that's 2 times 10 to the negative 3 meters squared. We also know the length of it, which is 40 meters. And we're looking for the resistance. So, our equation for the resistance of a wire is equal to the resistivity times the length divided by the area. We don't have to manipulate it around because we're already looking for the resistance. We just plug this stuff in. 1.72 times 10 to the negative 8 ohms times a meter times the length, which is 40 meters, divided by the area, which is 2 times 10 to the negative 3 meters squared. Plug that in your calculator. You get a resistance of the wire to be 3.44 times 10 to the negative 4 ohms. Take a look at this next example. Determine the resistance of a 15 gauge gold wire that is 5 meters long. The gauge number is how we rate the thickness of the wire. The higher the gauge, gauge, it's actually going to be the thinner the wire. In this case, the radius of that 15 gauge wire is 7.25 times 10 to the negative 4 meters. We know that the wire is made out of gold. So gold's resistivity is 2.44, oops, sorry about that, 2.44 times 10 to the negative 8 ohms times a meter. The length is 5 meters. We're looking for the resistance of this wire. So our equation is resistivity times length divided by area gives us the resistance. Well, for this particular problem, I'm not given the area. I'm given the radius of the wire. Well, assuming that the wire is circular, the cross-sectional area of it is the area for a circle, which is pi r squared. So we need to first calculate the area of this wire, taking the radius, 7.25 times 10 to the negative 4 meters, squaring it, and that gives us an area of 1.65 times 10 to the negative 6 meters squared. Now we know the area, we can plug it back into our original equation. So the resistivity is 2.44 times 10 to the negative 8 ohms times a meter. The length of it is 5 meters. And the area is, as we just calculated, 1.65 times 10 to the negative 6 ohms times, meter squared. This gives us a resistance of this gold wire to be 0.074 ohms. What you might want to do is try these problems out. We've worked out them in class, and pause the video, and then I'm going to put up the answers here, and then you can check them out on your own.